On an otherwise unremarkable day in 2004, Swedish television was experiencing some technical difficulties. I was made aware of this rather unusual video some time ago by a Swedish viewer on the off chance that I may be able to identify the equipment which ended up on the wrong end of that pointing finger. Well, we actually have that entire setup right here. Today, of course, we will be reflecting on the Analogue SPG and certainly its historic importance to television. And throughout the video, we'll also be having a look at television synchronization signals in detail. I think most people who watch the channel on a regular basis are going to have a pretty reasonable understanding of television synchronization signals and are going to know that ultimately it is an SPG which generates them. So a video like this certainly has the risk of ending up being rather boring, but not so fast, because of course when it comes to SPGs there are loads of interesting things that we can talk about. Before we start playing around with the kit, let's get our usual intro out of the way. Let's first talk about the problems that an SPG has to solve. To function correctly, all video signals in a television broadcasting entity must be synchronized. By now we all know this, but synchronized to what exactly? The very first requirement of an SPG is some kind of stable frequency reference, and there certainly are a few options. Virtually all SPGs have an internal frequency reference, and this may be anything from a synchronous electric motor to a high stability oven-controlled crystal oscillator. In addition to this, an SPG will have a number of external reference options which will vary depending on the vintage and the requirements. Synchronizing with the electricity grid was one of the earliest frequency references, but with the obvious drawback that the frequency tends to vary depending on the load placed upon the electricity grid. Beyond that, another common reference is a 10 MHz square wave or some other fixed frequency which may, for example, be coming from an atomic clock. Some SPGs accept a sine wave of a color subcarrier as a reference, typically either 4.43 MHz for PAL or 3.58 MHz for NTSC. And modern SPGs commonly use GPS. I actually demonstrated an SPG using GPS genlock back in video number 10. But the most important and frequently used reference input is for an external video signal. Now, once an SPG has obtained a reference frequency, it must then generate a set of synchronization signals. Now, we will look at all of these signals on the oscilloscope shortly, but first, let's just get a high-level view. Now, to build up our understanding, we'll first start off with a monochrome system. The two signals that everybody will be most familiar with are the vertical and horizontal drive, pulses which occur at the start of each field and at the start of each line respectively, pulses which can be found on basically anything that has a screen. Now next up we have mixed sinks, which is sort of a combination of the vertical and horizontal drive. In short, the mixed sink is a valid monochrome video signal of a black screen. Now last up we have the composite blanking, which defines the visible area of the picture, and that is it for monochrome sync signals. And by the way, here they are on the back of an actual monochrome SPG. Now let's add some color. The first new signal is the burst gate, which indicates the time slot where the color burst is inserted into the video signal. In PAL systems, an additional color signal is generated, the PAL ID, which indicates whether or not the phase of the color subcarrier is normal or alternate. In addition to the sync generator, a color SPG must also have a subcarrier oscillator. Like the sync generator, it must accept an external reference. For a master SPG, the color subcarrier is synchronized to the horizontal drive, and this is one of the most complicated processes which occurs inside of an SPG. We'll talk more about it later on. For an SPG synchronized to an external video signal, the subcarrier oscillator must phase lock itself to the color burst of that signal. Now, having generated all of these signals, what to do with them? Well, generate a video signal, of course. Now, virtually all SPGs will have some kind of internal video signal generator which makes use of all of the signals that we have just talked about. Now, the simplest, of course, is black and burst, but some SPGs may also generate more complicated test signals such as color bars. As you can imagine, all of this amounts to quite a lot of complexity, especially when you consider that the phase of the signals that an SPG generates must all be individually adjustable. Implementing such a device was a major headache in the early years of television. Designers of first-generation SPGs had to resort to mechanical implementations such as slotted rotating discs with optical pickups and even tone wheels, as this was the only practical way to translate between all of the various frequencies required. By the 1950s, manufacturers worked out how to build them using valves, but the resulting equipment was large, complicated, and very expensive. From then onwards, hybrid designs started to appear, reducing the size of the SPG to something more reasonable, and by the 1960s, transistorized designs were available. Many different companies have manufactured SPGs throughout history. In the early years, the market was served by companies from the ARC. But by the 1970s, a new player had entered the market, the Tektronix company. With significant resources, determination, and a clear product strategy, the US-based test equipment manufacturer quickly erased the competition, even in the PAL market. But they did not have it entirely to themselves. By the early 1980s, integrated circuits for building SPGs became readily available, diminishing their competitive advantage. But for all of this, the company held its majority market share well into the new millennium. It won't surprise you to hear that the company has since flogged its SPG business. Now next up, as I said, we're going to have a detailed look at all of the signals that we've just talked about. Now if you're not entirely familiar with them, that's probably alright, because you might not necessarily be alone. For any extraterrestrial in possession of the golden record attached to the Voyager 1 spacecraft, the analog television sync signal is the very first thing that they will need to get to grips with. Now for today's demonstration we have this PM5533. Now this is an item that was produced by Philips Broadcast in the Netherlands. It's actually a bit of Philips product management trickery. It happens to be the same product as the better known LDK4210, differing only by the controls and connectors which are populated. We also have this generator out on the bottom here for one specific experiment which we'll be doing shortly. Now the reason that we have this out is, as with the 4210, we have the full suite of ye olde sync signals available on the rear, which is certainly handy if you want to demonstrate them. Now as with before, we're going to start off with the 4 monochrome sync signals and we'll build up from there. Now what we're presently looking at is the vertical drive, and as we would expect, it's just a pulse which occurs at the beginning of every field. So we're going to switch on channel number 2, which is the horizontal drive, and as you would expect, it's a pulse which occurs more frequently, once per line. Now next up we're going to switch on the mixed syncs, and as I said, this is a valid monochrome video signal of a black screen. Notice that we can see the components of the horizontal and vertical drive contained within it. The inversion of polarity here is the vertical drive, but note that the duration of it is different to the actual vertical drive signal. Next, if we turn on channel number 4, this is the mixed blanking signal. Now to actually see what's going on here, we have to progress through the field a little bit. If we scroll over to here, down to about line 26, we can see that the polarity of this changes. So we start to see that it goes high momentarily. So if we just zoom in on that, we can see what's actually happening here. Now when this signal is high, this is indicating to any piece of video equipment that this is a time to be inserting your signal into the final output signal. So if we think about a monochrome camera or even a color camera, the tubes are always going to be outputting something, but we don't necessarily want that output in our actual signal. So this is really, as I say, this is really just saying to the camera, by the way, this is the time to gate your output into the signal that you're generating. So anyway, that's the monochrome 4, and next we will move on to color. Now for our color signals, we once again have 4 to look at, but it's 4 completely different signals this time, which I've hooked up to the oscilloscope here. Now I'm going to start off with the black burst, because I think this is just a signal which a lot of people are going to be familiar with. Now as I say, it is very similar to the mixed syncs. It really only differs by the fact that it has the color burst, and we can see it just starting to appear on those 2 lines there. So if we switch on our channel 2, this is our burst gate signal. So if we just scroll across a bit and zoom in on that, we can get an idea of what this is doing. There we go. There's a nice view of the burst gate there. So as you can see, that goes low whenever a piece of equipment is requested to insert its color burst into the signal. Now if we actually switch on channel number 3, we can see the color subcarrier, which is one of the outputs on the back of this SPG. So, just looking at this, we can see for a piece of video equipment which has all of these individual sync signals available, just how ridiculously easy it is to compose a video signal. And if we switch on channel number 4, we have that special PAL-specific signal. This is the PAL ID, or some people call it PAL index, which is basically indicating whether or not the phase is inverted or alternated for this particular line. As we can see that it's a square wave that changes polarity on each line, as you would expect. Now, trucking all of these signals around in a studio is obviously pretty expensive and requires a ridiculous amount of cabling. So this old-fashioned, just all these different signals, this is something that really only persisted probably until the end of the 1970s, maybe into the 1980s. Beyond that, you start to get silicon, which can actually deconstruct the black burst signal into all of these individual signals. So all of this just craziness with all these different signals became completely unnecessary and rather old-fashioned. Now next up, a bit more about that relationship between the color subcarrier and the horizontal drive. Now I could just throw a bunch of equations at you and say, well, you've been told, but I prefer a more practical explanation. Now if we have a look at the color burst here and just trigger on a horizontal sync pulse for every single line, what we see is just this envelope of a signal, and we're seeing the phase of the color subcarrier at hundreds or even thousands of different rotations, and it looks a bit random, like there's no relationship at all. But as I say, there is a relationship, and we can improve our view a little bit here by selecting a particular line. So now we see it at 2 different rotations. But we still can't see the color subcarrier and the horizontal sync in phase. Now I think the best way to explain it is to talk about the 8-field sequence for PAL or the 4-field sequence for NTSC, and what this is saying is that the phase of the horizontal sync and the color subcarrier only meet up once every 8 fields, or 4 for NTSC, as I say. Now to actually witness this on the oscilloscope is a little bit difficult, and this is why we have this this generator out here, because what we need to do that is what's known as certainly what Philips referred to as a frame 1 sync signal, which is a rather difficult thing to come by, but we do have it available here. And the 5533 is presently genlocked to this generator, and we have the frame 1 coming into the oscilloscope here. So what we can do is change it to trigger on that. That's going to be on channel 4. There's going to be an edge, and there it is right there. So there it is. As I say, this is quite a rare sight there. That is the color subcarrier, or the color burst, in phase with the horizontal sync. Now this frame 1 sync signal is fairly infrequent, and it occurs at a frequency of 6.25 Hertz. Now this is actually a great opportunity to talk about what the subcarrier phase control does, which you will find on certainly a lot of old analog studio equipment. So if we trick this pot here, we can see that the phase of the color subcarrier is actually rotating. And it's rotating in relation to the phase of the subcarrier, which is coming from this unit here. So that's really the purpose of it, is to adjust the output of this generator relative to this one, and that's probably all that this control will do. If this were free running, you probably find that this pot here doesn't do anything at all. A rather interesting implication of all this is that the shortest possible recording of PAL video, which can be played on a loop, is 4 frames, or 2 for NTSC. And take a minute to think about the implications for video tape recorders, where you are trying to do a synchronized cut from a live feed to tape, and your color subcarrier is on tape and you have no control of it. Anyway, that's a topic for another time. Now next up, we're going to take what we've learned about SPGs and use it to perform a little experiment. Now the experiment is going to be to synchronize two PAL video sources to this SPG here, and then we're going to fade between them. But fade with what exactly? Well, this device here, of course. Now it turns out that small portable video mixers which are designed for working with synchronized video signals don't exist. Now you can get small mixers which are designed for unsynchronized signals. Now these are for hobbyist use. What they do is they take the analog signals in, digitize them, mix them digitally, and then they convert back to analog again, which you know, is a very complicated device, but doesn't require any skill to operate. Whereas mixing video signals with a purely analog device like this one, this is actually quite difficult, and this is really what we want to talk about in today's video. Now, our video sources in question are firstly going to be everybody's favorite, the PM5534, and secondly, we're going to be using this AJA Kona Video I/O, which is in this Thunderbolt enclosure here. Now, one annoying limitation I discovered with this device when I was making this video is that the phase of the color subcarrier on the composite output is fixed, which is not ideal, and I would say probably rules it out for serious analog studio use. To get around this problem, we're going to be using a professional PAL coder, this PM5638. We'll be feeding it with an RGB signal from the Kona, and then we will take our PAL composite from this unit and mix it with the 5534. Now, before we can use the Kona with this PAL coder, there's a little bit of setup that we have to do here. Now, presently, we're looking at the AJA color bars, and that's coming from the Kona through these three RGB cables, and I had to move the unit because my computers are over on the other side of the room. Now, looking at the screen here, everything looks fine, but if we have a look at this oscilloscope, well, it's not really working. I mean, I've set up a video trigger here on channel 1, which is the composite output of this unit, but it's not triggering. What the heck's going on? Well, if we move the trigger to channel 2, which is the green output from the Kona, move that to an edge. Well, we can see we've got a bit of a problem here. So the yellow trace is the composite output from the PM5638. The blue trace is the green output from the Kona. Now notice that we have this nasty spike in the middle of the sync pulse from the color coder. And you might be tempted to think there's something wrong with it, but there isn't. There's a number of different ways that we can sort this out. We could take an extra burst output from the SPG and apply an offset to it. We could tweak the horizontal timings in the AJA control software. But the most convenient and arguably correct way to sort this out is to just jam a screwdriver in the horizontal phase pot on the front of the color coder and just tweak it. If I can just find the actual screw here. There we go. So and just pull that in like that and just line these up nicely. Let's check the other end of it. Yeah, probably about like that. So now it's time to start performing the lineup so that we can actually fade between these two video sources. Now I have to stress, what I'm about to attempt here in no way represented any real-world operating procedure. This is purely just so that you can see what's actually going on. Now we've got, from our SPG, we're presently using two black burst outputs. So black burst 1 is feeding the Philips generator, and that's what we're seeing on screen right now. Black burst 2 is headed to the AJA Kona and this color coder, which we just set up. Now our Philips generator and our black burst output 1, we're treating these as a reference. We're not going to touch them. This is a good signal that we're going to align to, and certainly not, as I say, not play around with at all. So what we're going to do on our master SPG here is go into the menu for black burst 2, and this is where we will start to play around with the timing. So first things first, let's just adjust the fader on our video mixer so that we can start to fade in the output from the AJA Kona, which as you can see is a Philips pattern. Now the AJA doesn't have the ability to generate a Philips pattern built in. What I've done here is gone onto the Wikipedia page and grabbed this plot here from the PM5644G00, and this is the PAL 4x3 model. This particular plot has been sized so that you can basically feed it straight into the AJA control panel software, and certainly that will allow us to get a geometrically accurate Philips pattern from it, but as I say, it's not going to be a true Philips pattern. Now what we need to do to start lining this up is go into the timing menu. There's three settings here: vertical, horizontal, and T, which is this is basically the timing within a line, so that's the horizontal phase. Now this is the only one we need to adjust because our error is relatively small here. So we're just going to start incrementing numbers and see what happens. Now on the oscilloscope here, you can actually see all the three signals of interest. So the yellow one is the output of the video mixer, the blue one is the Philips generator, and the purple is the AJA Kona. So as you can see, as I increment this, they're starting to line up. And now the particular feature that we're actually looking at on this scope here is the three white lines in the center of the image. I just picked those because they're a nice monochrome feature, which is easy to look at on the oscilloscope. And we certainly want to be aligning on a monochrome feature because aligning on color features is not really, not quite so easy. So if we zoom in on the oscilloscope now and just play around, so the outputs are not absolutely identical, but I would say that's probably about it there. Looks pretty well lined up. It's hard to say with the outputs. Actually looks a bit nicer in that position. I'm going to go for that position there. I mean, it doesn't matter a huge amount. So now if we have a look on screen, we can see we've got both outputs. We can see the 5534, we can see its clock there, and we can see the output from the AJA Kona, which if I just bring the wiper all the way around to this way, you can see it right there. So there's our sort of Philips pattern, but it's not really a Philips pattern. This is just the image of a Philips pattern, but a reasonably geometrically accurate image of one. Alright, so next up we have to sort out our color subcarrier phase, and if we look at the screen here, we can see this flashing, and this is instantly indicating to us that we're not in phase. The flashing areas are the achromatic fields on the Philips pattern. This is a deliberate phase error which is introduced for testing PAL decoders. And it does actually happen to be a pretty good way of seeing whether or not you've got a phase error when you're trying to mix two signals. Now if we actually have a look on the oscilloscope here, we can actually see that phase error straight away. I'll just scroll across here. So remember that the purple and blue are our two inputs, and you can see that they're not aligned. Now the feature that we're looking at here is that pulse there is this white line, and this is that piece of green there. Now I do apologise, I don't have a vector scope, which is how you would normally set this up, but we can sort of do this on the oscilloscope. So if we run this again, and we'll just jam our screwdriver into this subcarrier phase, screwdriver hole here, and just rotate it around. Now we're going to play around with it quite a bit actually. Notice the amplitude of the output actually changes depending on where I position this. And hypothetically you could get to the point where the two subcarriers cancel each other out actually. And probably don't have that level of adjustment, but theoretically, oh yeah, we could. So we can almost pretty much kill off all the colour. Not quite. We can nearly kill off all the colour. So anyway, if we rotate this around, we should get to the point where they're actually quite well lined up, and we can see that just by looking at the achromatic fields there. That looks looking pretty reasonable. So if we just do some single sequences, we can see that they're pretty well in phase now. So yeah, so that's why you want to have this subcarrier phase, because if you don't have it, then you have to start doing other mucking around to try and do this. Very nice to have this here. Alright, so only thing left to do now is just a quick demo. So we're presently looking at the Philips generator, of course, and the Kona is playing some appropriate content which won't get me into any trouble. And I've also moved our ramshackle video mixer just in front of the telly here. So now we can just slowly fade in to our other video. There's a little bit scratchy, unfortunately, the pot in here. This is an old wire-wound pot from decades ago, but yeah, it fades in quite nicely actually. So there we go, there's our video which we're playing through the Kona. And we'll just slowly fade it back again. Lovely. So there you have it. two video signals pretty well perfectly gen-locked together, but as I say, not perfectly mixed. This video mixer, it's got its issues. It doesn't really have particularly good balance. So for example, when you've got the pot in the center, the amplitude of the output signal is quite a bit higher. I did think, should I try and solve these problems, but I can't be bothered. I mean, it's good enough, you get the idea. I think this was the most downvoted video I think I've ever uploaded. I presume that was because people didn't like the music. There were a number of comments complaining about that. So yeah, lesson learned. I won't have any more silly music in any of my videos. So now we're going to take a minute to talk about the events which unfolded on that fateful day in 2004 at Swedish television. Now, as I say, I do have the same setup which they had here. Looking at the video though, theirs appear to be branded Philips, which would indicate that those units are considerably older than these ones. However, they are the same equipment. Now the setup basically is that you have two SPGs, which hypothetically should be identical, same options populated, same configuration, maybe in genlock. These are genlocked. And the outputs of each are connected through to the changeover unit. And the changeover unit's job is to switch between the two SPGs. So if one fails, then it should switch to the backup unit. That can either be automatic or manual. And the way that it knows to switch over is because the internal circuitry inside these SPGs extensively monitors everything that's going on here, all the outputs. If anything goes wrong, they will assign a fault signal through a special cable to the changeover unit, which will then know that something has failed and it will switch it over automatically. Now in this particular setup, I've only got one output from each SPG connected to the changeover module, and that's the one which generates complex analog test cards. So you can see it on the screen right there. We can see that SPG1 is this top unit, and the bottom unit is SPG2. So now we can demonstrate what is supposed to happen when something goes wrong. Now what I've got here on the end of this cable, this is connected to one of the black and burst outputs on this top SPG, which is presently doing nothing. Now I can make a fault happen by just attaching this BNC shorting cap to this connector here like this. So as you can see, we've got an error on the screen, level error at black burst 2, and this horrible beeping sound which is indicating that something has gone wrong with your setup and you need to go and do something about it. So let's just go and reset that and take off the shorting cap. Now it's actually switched back to the original. So that's what's supposed to happen. Now what actually happened at SVT is not entirely clear. The video which was sent to me does have an interview with the technical director at the time, and that was actually kindly translated to English for me. Apparently YouTube can't do that itself yet. Unfortunately, not much information was actually disclosed in that interview. But privately, I have heard that what happened is they lost the changeover unit and they lost an SPG, both at the same time, somehow or other. I'm not actually sure how that's even possible. And the reason they were off air for 45 minutes, well not off air, but on air in a rather chaotic way, is that firstly they were scrambling to try to get the changeover units to switch over, but they couldn't because it was faulty. Now when they realized that they couldn't make the changeover unit do its thing, they then resorted to running around the back of these items and pulling all the cables out of the changeover unit, and basically connecting the entire studio to their backup SPG, and eventually got things back up and running again. So yeah, a pretty disastrous situation there, and just ridiculously unlikely that that would actually happen. And I feel like there might be some additional details attached to that incident which I'm not presently aware of. But anyway, there you have it. So that's what I presently know about that, and a quick explanation of what this is all about. Well, that is all for this video, and as always, I hope that you found this interesting. At the time that I'm recording this, it is just days away from the BECG's September opening days. If you're from the UK and happen to be in the area, definitely stop in and have a look. you will probably be able to see the LDK4210 in action and driving various camera systems and other equipment. Or perhaps you won't be quite so lucky because they've become overly frustrated with all of the faults that these things tend to develop and chuck them out the window. But nonetheless, you'll certainly see something like this in action, and certainly relevant to everything that we've talked about in today's video. Anyway, as I say, that is all. Thanks for watching.